For those of you who don't know me, I really hail from the polymers and 3D printing world. So just additional points about my background. I received a bachelor's in chemistry from Stanford University, then went on to get a PhD in chemistry and nanotechnology from the University of Washington. I, from there, spent a couple years going back to Stanford, working as a postdoctoral research fellow in the chemical engineering group, and then spent a few years in consulting, really working on plastics and adhesives in consumer products, as well as medical devices and electronics. And then entered the 3D printing space as director of materials at Origin, which is a startup company founded by ex-Google and ex-Apple software engineers, and was recently acquired by Stratasys. So here at Myerson, we've been a company that's been around for over 100 years, developing and offering dental products to the industry. And our mission in dentistry is really to provide quality products and exceptional service to enhance smiles and the overall health of patients globally. As far as our vision in 3D printing, we are entering the space with a bang. I'll talk about that in a little bit later. We're also going to be the leading dental company in the world, which is our goal, in order to offer 3D printed final restorations that are both beautiful, but also long lasting. You may be familiar with some of our current material offerings. I've listed some of the names here, some of which are Duraflex, EMA by Myerson, the Dentivera milling disc, as well as the Permasoft denture liner. And there's a variety of others as well. I didn't want to list them all here on the slide, but it's important to note that all of these materials are thermoplastics. And for the bulk of my talk today, I'm really going to focus on thermoset polymers or photopolymers that are 3D printed. As far as Myerson, I'm proud to say that we were the 2020 Emerging Technology winner as awarded by RadTech, which is the trade association for both UV and EB curing chemistry. So we're really excited about the photopolymers that we're developing, the resins for 3D printing. Now, I like to take a step back when we talk about 3D printing and just sort of make sure everyone's on the same page about the benefits. Also, this is super critical given some of the supply chain issues we're facing currently. And really, 3D printing offers a variety of different benefits to those of you who are printing chairside or printing in the lab. And the first and foremost of those is really the on-demand manufacturing aspect, where you have localized manufacturing, you have on-site manufacturing, and really being able to produce the parts close to your office or wherever to really get them to the patient faster. 3D printing also enables rapid prototyping and iteration, where you can print the part, you can fix the design, you can then print again. And it also gives you the ability to print varied designs that really aren't possible with injection molding and other manufacturing methods. And this really primes 3D printing for customization applications, specifically when we think about appliances for different patients in the dental industry. I also like to point out that 3D printing for production is happening now. The pandemic was actually a really big catalyst for the 3D printing community. Different entities coming together to print replacement parts for ventilators, to print nasopharyngeal swabs for COVID-19 testing, as well as a variety of other components. But really, the thing that has catapulted 3D printing to be really prime time now for production applications are the materials. In the 80s and 90s, the materials were largely acrylate based. They were brittle. They took on a lot of water. They didn't print accurately, or they didn't hold their shape. They're really great for prototyping. But in the present day, we have much better materials that have improved strength, durability, less shrinkage, less moisture absorption, good temperature resistance, and really exhibiting those key properties that enable commercial grade parts that can withstand the elements that the parts and materials encounter when in service. In addition, now there's better print technologies. This comes in the form of improved printer components, projectors. These things together really yield consistent processes. And as a result, we're starting to see commercial grade part quality in a variety of applications in addition to dental. So there are, the bulk of my talk is going to focus on polymer-based 3D printing and specifically photopolymer-based printing. But it's important to highlight, for those of you who may not be as familiar, the other polymer-based 3D printing methods. And I really love this graphic from Formnext, which is a big trade show in 3D printing held every November in Germany, because it really does a nice job of summarizing the different 3D printing technologies that are out there for printing polymers. Starting at the left, we have powder bed fusion, where you have techniques such as multi-jet fusion or SLS, selective laser sintering. There's also different material extrusion technologies where you have fused filament fabrication, or also known by a trade name of fused deposition modeling. And then companies like Arberg that are taking resin pellets traditionally used for molding and heated into a melt flow are actually being 3D printed instead. And then toward the right, we have kind of three general photopolymerization methods. The first is material jetting. You can sort of think of this as inkjet printing, where you have a liquid resin and you're using a technology similar to inkjet printing to print the 3D printed parts. And then there's two other main types of photopolymerization 3D printing. The first being stereolithography, or SLA, where we typically think about this as you're curing with a laser. So you start again with a liquid resin, you cure with a pointed laser to form the three-dimensional part that you desire. And then lastly, DLP, which is digital light processing or digital light projection, also direct light processing, a couple of different synonyms there. But in this case, you have a light projector that's giving off the UV source, and you're curing in a two-dimensional layer by layer to form your final part. And I've highlighted here at the bottom a variety of different 3D printing companies that are utilizing photopolymerization printing. And what's important to note is that even though there's really these key 5 or 6 technologies that print polymers, and the 3 that print photopolymers, these companies all have a slight variation on this technology, which makes them unique. For example, you have Carbon that has a digital light synthesis technology that's used in their printers. Azul 3D, for example, you have a high area rapid printing technology where they're really focused on printing larger parts, but printing them very quickly. And then companies like Nanoscribe that are using 2-photon polymerization to even print. So there's a variety of different companies out there that are using photopolymerization technology, and just with a slight difference in their hardware and software that are enabling the printing of these different parts. So before kind of delving more into the photopolymerization printing, it's important to just touch on the other techniques that I mentioned. For FFF, or fused filament fabrication, this is essentially from a high level where you have thermoplastic filaments that are extruded through a heated nozzle to form the desired printed part layer by layer. And as an example, I'm showing Prusa's printer on the right, where you see the filament spools at the top, and they're printing the figurine shown in the middle of the image. Now, there are some advantages to this method. It's more affordable, it has a smaller footprint, and the thermoplastic materials that can be printed really have a wide range of properties. And really, you're able to print more of those commodity plastics that are used in a variety of different applications and for printed part and for different parts. Some of the disadvantages, however, are that it's a slower technique. The parts tend to have poorer resolution. They're really not suitable for mass production. It's, you're only able to print one part at a time. And given the speed, it's really not suitable for printing, nesting a lot of parts and printing a lot at once. As far as another polymer-based technique, powder bed fusion, and specifically selective laser sintering, or SLS, is where you have a laser that's aimed in the build space that's defined by a 3-dimensional model. you sinter a polymeric powder, say like a polyamide or a nylon, to form your desired part. Now, the advantages of this are that the structures are self-supporting. You don't need to print the supports, and the materials have good mechanical properties. However, these tend to be really large industrial systems with big footprints. As a result, they're quite expensive. The parts, as you can see from the example parts shown at right, they tend to have a grainy surface finish. There's some difficulty printing some features, say a large flat surface or small holes. And I'm showing here just for reference kind of the Anexa 3D SLS machine. You can see it's quite big on the footprint. This is probably my one metal 3D printing slide. I tend to be a polymer 3D printing nut, but it's important to understand just from a very high level metal 3D printing, how that works, and to compare to polymer-based 3D printing. So really, it comes down to it. There's three main metal 3D printing technologies: SLM, or selective laser melting, direct metal laser sintering, and then binder jetting as well, or is another main one. But all in all, really what you're doing in these technologies is taking metal particles and you're fusing them together upon melting with added pressure. Now, the advantages are that almost any geometry can be created. And then you can also go on to machine and coat the parts as you would if they were produced from any sort of traditional manufacturing method. However, some of the pain points are that you have a really high cost of material and printer. You need support structures, and then these materials can be kind of heavy in the mouth for different dental applications. I'm showing here a really nice part from EOS and cobalt chrome, showing some different dental crowns there. So if we take it back to the UV photopolymerization methods, again, a lot of them boil into kind of two categories, where you have the traditional laser stereolithography, and you have the digital light processing or direct light processing with the printing with the projector. And I'm going to spend the majority of the rest of my talk talking about photopolymerization and 3D printing, and kind of why that's the more desirable technique when you're looking to print for different dental applications and clinical applications. So taking just a step back on photopolymers in general, some of you may not know this, but photopolymer materials actually represent the largest technology segment and create the biggest revenue in the additive manufacturing market. They're reported to capture over half of the market for polymer materials used in 3D printing. And it's estimated that photopolymers will contribute about 1.7 billion in revenues in 2022, according to the Tactile Report, which is a report that I authored late last year, exclusively focused on photopolymers and additive manufacturing. Now, if we take it back to basics, really what you're doing when you're doing a photopolymerization is you have a liquid resin, comes to you in a bottle, but when you look microscopically, nanoscopically on what's happening in that resin, you have a variety of different molecules that are at play and interacting with each other. You have some oligomers, which are really, you can think about as short chain polymers. You also have monomers, which are just sort of one component of a polymer. And then you have photoinitiators that react with the UV light to kick off this photopolymerization reaction. So while you start with a liquid resin, once you apply UV light, these reactions take place on a fast timetable, typically less than a second or seconds. And then you have a cured solid thermoset polymer, which gives you those really desirable properties for end-use applications. It's also important to think about the chemistries that are involved in these photopolymerizations. Typically, you have a couple of different mechanisms of polymerization that occur. Generally, in most cases, these are a free radical polymerization or a cationic polymerization. And as far as the components within the resin formulation, generally speaking, you have those oligomers that I mentioned. They're typically present from 25 to 90% of the formulation. You have monomers, which are present in 15 to 60%. And then you have photoinitiators, which are present in 2 to 6%, a little less, that kick off the reaction. You also have additives and fillers. Those can be present in between 1 and 10%, depending on the resin and formulation. Now, the other thing to consider when you're working with photopolymer resins is that different printers cure at different wavelengths, and it really depends on the light source that's included in the printer. So you can have a printer that has a light source that cures and emits light at 355 nanometers. You can have a printer that emits light at 385 nanometers or 405 nanometers. And the 385 and 405, I would say, are probably the most common for commercial printers, but there are other wavelengths as well that are out there. But your resin that you're using is typically formulated for a specific wavelength. And this is because of the photoinitiator that's included. And sometimes you also need a sensitizer depending on the photoinitiator that you're using and the overall general formulation. So this is part of the reason mainly why you can't take any 3D printable resin and use it with any sort of printer interchangeably. It's the reason why there's typically validated settings as well as a validated post-processing workflow, which we'll talk about in a little bit as well. Now, as far as the different kinds of categories of chemistry, you can have 3D printed resins that are acrylates, epoxies, polyurethanes, polyolefins, silicones even. And then you also have hybrid versions incorporating 2 or 3 different types of chemistries. But what's really exciting are the new chemistries that are being deployed in 3D printable resins. And I'm going to talk a little bit about some new chemistries coming online from Myerson later on in the talk. So some of the advantages, why UV curable 3D printing? I mentioned some of the advantages and disadvantages of those other techniques, but really when you're talking about UV cured materials for 3D printing, you really have a chemistry chamber at your disposal in the printer. You have the control and the tunability that you can achieve within the print chamber. You also have rapid curing of UV-enabled polymerization, which yields fast printing speed in building parts. And specifically in DLP type processing, also known as a vat polymerization, where you're starting with a vat of resin. You're able to nest a lot of different parts depending on their size and depending on the printer together, so you can print them at once. This is great for if you're in sort of a laboratory or production environment and you need to get a lot of parts printed at once. You also, as I mentioned, can utilize a wide variety of monomers and resin systems. And this is really what gives you a vast array of mechanical properties, allowing for use in different applications. And really, the speed and throughput that you achieve are important for manufacturing at scale. And I'm showing here just a screenshot of a Sega's DLP printer, which is heavily deployed within clinical, dental, and also dental laboratory environments. So I also want to touch on inkjet 3D printing. This is a really cool technique as well, because you're basically taking a technology that was used to use inkjet to print paper, and you're applying it to 3D printing. In this case, you have inkjet print heads that are used to print photopolymer resins onto a build platform. Some other synonyms for this type of printing are jetted photopolymer, material jetting, or even photopolymer jetting. But some of the really cool advantages about this are that you can do multi-material printing and you can do multicolor printing. I'm showing here a really nice part from Stratasys where you can see the multiple colors in a singly printed part. You also get great detail in the prints. Now, some of the disadvantages are that these tend to be large, expensive machines. You also need to incorporate supports from a different material. And sometimes the materials, because the properties are good, sometimes they can be a little expensive. So we talked a lot about the different print technologies, but I like to say the dirty little secret of photopolymer printing is the post-processing. And really the post-processing, so after you perform the print, is where you can derive a lot of the key mechanical properties in printed materials. So the print chamber, we talked about being a chemistry vessel, basically curing different parts at the completion of a print. But after that, especially when you're using a DLP type printer, you're sort of left with this part dripping in liquid resin. And you have to take a few steps to be able to say, oh, here's my finally completed part that's ready for the patient. So a lot of DLP and photopolymerization-based printers, you can use the printer to basically get a part that's just about fully cured. And you may just need some additional UV light at the end to get your finally, printed part that's ready for prime time. But depending on the chemistry, sometimes you need a heat treatment. And this can also help to either activate another mechanism within the polymer, or it can help to create durability, or it can help increase strength, or a variety of different properties that are desirable. But the great part about post-processing photopolymers is that rarely sanding or any additional mechanical treatment, as you have to do with other techniques, is needed. So what's an example of this type of post-processing and why it's important? So, if you recall, sort of last year in the pandemic, before the vaccines came online, COVID-19 testing was very prevalent, and the use of nasal pharyngeal swabs for this were in great demand and widely employed. Now, with the 3D printing of nasal pharyngeal swabs, there's actually guidelines for the post-processing that are outlined by the FDA. And the reason for this is because a very methodical and consistent post-process is needed in order to have these nasal swabs perform as the way they're intended in the application consistently. So it's really important to have a consistent workflow with post-processing to achieve consistent end properties in the application. And so if you receive a 3D printed resin and there's instructions for use or optimized settings or optimized post-processing protocol, that is generally the result of a lot of validation that's been done in order to give you the mechanical properties that are advertised on, say, the technical data sheet for the material. So it's just important to keep in mind, there's some things you can do to ensure you have a more consistent post-process. Some of this is comes down to the equipment, how reliable it is. If you're able to post-process multiple units in a batch, you can also use automation and different QC methods to ensure that you are using a consistent workflow and a consistent post-process. So when you're working with resins, there are a couple of things to keep in mind as far as formulation considerations. When you have the resin in a bottle, there's a lot going on there, especially when it's in the printer. You're doing that post-processing like we talked about. Now, a lot of times the formulations I mentioned are specifically tuned for a specific wavelength, but also they're optimized for through cure between the layers, especially in the case of DLP. And that's really to minimize defects such as cracks or pores that can occur in the material. And one thing I like to note is that companies are routinely working hard to reduce the cost per part, the cost of the resin, and improve the speed and throughput so that these resins are ideally tuned for production applications. So we spent a lot of time so far talking about photopolymers in 3D printing and the different technologies that are used, as well as post-processing. I want to shift gears now toward dental and how photopolymers are being used in the dental space currently. And I like to just comment on, the evolution of using 3D printed materials for dental. At first labs had started to 3D print models and then kind of shifted to using intraoral scanners to generate impressions. From there, printing wax for crowns and bridges and swapping that with ceramics and gold was an application. Surgical guides have also been printed where the doctor can use those guides as a path to drill for implant placements. Also printing of night guards and splints, temporary restorations, and then now recently printing of teeth and base for dentures, as well as using these types of 3D printed materials not only for temporary placed dentures, but also permanent dentures, which is really exciting. Now, as far as the clinical applications of 3D printing in dental, there's a variety that I'll describe that I think are perfect for photopolymers in dental. And it's important to note that while the dental industry was an early adopter of 3D printing, new materials and more advanced printers are actually what is responsible for enabling the achievement of a wider range of applications that really were not possible before now. In addition, 3D printing offers the customization needed for dental service laboratories, as well as offices chairside. So kind of the first example of a clinical application is the monoblock denture. In this case, showing an example on the right, a virtual file is generated in CAD for the tooth setup in the digital workflow. You then have an STL file that's used to 3D print a monochromatic and monolithic denture that's used to evaluate clinically the basic aesthetics, the lip support, as well as the vertical and horizontal records of the patient. Orthotics and night guards. Here, showing some good examples at the top. Here you have an intraoral scan of both arches and an occlusal or bite relationship. And then you can also employ a 2mm thickness that can be programmed for the orthotic, and an STL file then generated for a maxillary night guard. And I really want to thank Professor Steve Sadowski for these clinical application slides that he created. Another example, you have 3D printed casts of implant analogs in place. Scans can first capture intraorally the report of the three-dimensional relationship of implants with respect to the adjacent teeth. You then have STL files that are sent to the dental lab, and then you have the analog that is cast and sent to the dentist with the definitive restorations in place. A great application for 3D printing. 3D printed models for toothborn restorations. Here you have an intraoral scan of both arches that's completed, including preparations for an 8-unit bridge that's shown. You can then scan for the bite relationship next, and then you have STL files that are used to generate the models. And in the images, you see the models up top, then you see the actual patient's mouth without and with the preparation as a comparison. Another really hot application right now is the 3D printed maxillary arch and how that's used to thermoform a clear aligner. So in this case, you have an intraoral scan of the maxillary arch that generates an STL file, and then you have a 3D printed cast for clear aligners to then be fabricated. There's also things like a direct print aligner that people are working on where you can kind of skip the thermoforming step, but then just directly print your transparent material for a liner, which is also a really exciting application to think about, especially if you can print this chairside in the dental offices. And finally, 3D printed try-in to verify fit, occlusion, and morphology. This is an economical procedure to evaluate a critical aesthetic for the appliance in the patient's mouth. And also employing 3D printing for this application allows a reversible state before the definitive restoration is fabricated. So it's really a great way to determine whether what you've created, if the final restoration is actually going to work with a sort of a temporary version of it. Now, with all of these different applications, really the key to expanding upon these applications and including others are new materials. New materials are critical to enabling expanded clinical applications and new applications. And with that, I'd like to introduce Trusana by Myerson. Trusana is a resin that will be available later this year that is really targeted for printing of teeth for denture applications. Also, we'll be having a denture base material coming out in early next year. Now, Myerson's been working on this product for a while, and it's really, really important to understand that what goes into this product is, number one, true science, where we have some unique chemistries that haven't routinely been employed in dentistry, but really are highly scientifically designed to give the durability and the strength required for applications in the mouth. In addition, I'll share some data with you on Trusana, where we can deliver high strength that's even maintained after exposure to water. As a result of this Trusana chemistry, there's also resilience and toughness that come from the product, and really able to withstand different elements or environmental things that you might encounter with a patient using the appliance made from Trusana. So it's something we're really excited about. So not only is it based on good chemistry, good strength and toughness, but also Trusana shows very aesthetically pleasing and is beautiful as far as the comparison to even real teeth or other premium denture products that are out there. And I'll show you here an example where we have printed teeth. We also have printed gums, all from Trusana. And you can really see the different transparency in the tooth. You can really see, compared to a shade guide, how on point the shade is. And what we've been doing is evaluating this material with different beta labs, getting some really good feedback about the ease of workflow compared to other dental resins, the aesthetics, how on point the shades are, as well as the ease of working with the material. So it's something we're really excited about, and I'll tell you a little bit more about the mechanical properties here in a bit. Again, just showing here some of the 3D scans of Trusana teeth, and then also the resin will be available on different printers, including the Asiga, the Sprint Ray, and then also working on the Roland Accurata as well. So the plan is definitely to have Trusana available for a variety of different printers, and really the Sprint Ray and Asiga to start. Just another example, here we have the Trusana denture base shade. This is the light reddish pink shade, prints perfectly, looks great. Really exciting to see, you know, a premium 3D printed tooth product that has some of these aesthetics. It's not really just the aesthetics though. I mean, it's the mechanical properties that we observe. You know, what we did as part of our analysis of Trusana is we measured the Flexural modulus and we compared it to the leading 3D high impact resin. And the results are great. And I want to mention too that the results I'm showing you were conducted and verified by an unbiased third party. So these were done out of house. And really what we see, if you test the Trusana material dry, so without any water exposure, you get 3.6 gigapascals of Flexural modulus. And if you compare that to the leading 3D high impact resin, it significantly outperforms. Now, the next thing we did in our testing was to submerge these parts of Trusana in water for 48 hours, still outperforming the competitor. Then we took it a step further and submerged these parts for 14 days in water. And still, not only is Trusana pretty consistent with a Flexural modulus remaining around 3.4 to 3.6 gigapascal, but the competitor leading 3D high impact resin actually decreases in the Flexural modulus as you increase that exposure to water. So this is something we're really proud of and is really a function of the chemistry and how it functions. Same with the Flexural strength. If we look at dry samples of Trusana, we have a Flexural strength of 139 megapascals compared to the leading 3 high impact resin, 73. If we move again doing that 48-hour water submersion test and then testing the mechanical properties, the Flexural strength pretty much remains consistent at the high 130s. Again, we did the same test, exposing the resin printed parts to water for 14 continuous days. And again, the Flexural strength remains compared to the other material where it steadily decreases. And these results as well were performed by the same unbiased third party. So we're really aiming to show on the spec sheet, you know, you get the properties that are advertised with Trusana. So not only are the mechanical properties performing very well in class, but the water uptake is also quite remarkable. or the lack thereof, I should say. So if you have a current generation of 3D printable resin, the water uptake tends to be around 2%. If you take a standard denture tooth, the water uptake tends to be around 0.4%. But with Trusana, the water uptake is 0.35%. And so that's part of the reason why we're getting such good mechanical properties, even after the 14 days of water exposure. Something we're really proud of with this material. I can't mention mechanical properties without at least mentioning wear depth. So what we did is looked at an economy tooth as a comparison and performed some testing. You can see that the wear is quite high comparatively. We also took a premium tooth, looked at the wear testing, and while it's much lower and on par with lithium disilicate, if you compare Trusana with these other three materials, the wear around for the same amount of time is actually about half or much lower. And again, these results are performed by a third party out of house as a comparison. So in summary, these are the cured material properties for the Trusana resin. We mentioned flexural strength and modulus. I'm showing here also the tensile strength and modulus. And it's important to note as well from this slide that each one of these methods were performed according to ASTM or ISO standards. I also like to highlight that as part of our development and what we're currently doing is testing with different universities. So universities such as Loma Linda School of Dentistry, the UConn School of Dental Medicine, the UCSF School of Dentistry, as well as the University of the Pacific, are all trialing Trusana now for different cases. And we're looking forward to getting that feedback. So far, it's been really positive, and more of that will come in over the next several weeks. So if you're wondering, when can I get my hands on some Trusana? It is going to be available in this year, the tooth resin. I would say in the next couple of weeks, where our premium denture tooth resin will be available. And then in 2022, we'll have a high impact denture based resin available as well. And as far as the printers that you can print Trusana on, initially will be the Sprint Ray printer, and then also the Asiga printer. So something we're really excited about. And if you're curious about photopolymers in general, used for additive manufacturing and want more information, I invite you to take a look at the Tactile Report, available at tactilereport.com. This gives a lot of different key players, materials, printer technologies, as well as opportunities and trends that are happening in the photopolymer additive manufacturing space. So if you're interested, feel free to check it out. So I'll just leave you with this. Trusana was definitely a labor of love developed over a long period of time. We're excited it's finally here. We're excited about the mechanical properties. And really, the resin itself has the strength and toughness required for these different dental appliance applications, coupled with the beauty and the aesthetics that are required to actually serve as printed dentures. So I invite you to take a look further at Trusana, and also invite you to follow us on social media. We have Myerson on Facebook, Instagram, as well as LinkedIn. And this is really the resource too, where you're going to find a lot more information in the next coming weeks about the launch of Trusana, more information, and then when it's available for purchase. So with that, I'd love to take any questions you might have. If you don't ask them today, my email is stephanie@myersontooth.com. I'm happy to answer your questions offline. And thank you so much for your attention.
Thank you so much, Dr. Benight. We do have a couple of questions. The first one I'll be able to answer because one of the attendees wanted to know if we are recording this and if they can get a link to it. It is being recorded, and you will be able to view it at any time on YouTube and Zahn Academy. So I hope that answers your question. The first question is one wavelength better than the other as far as 355 nanometers, 385, or 405?
It's a good question. I would say that it's not necessarily better. I would say that the 385 and 405 nanometers are more prevalent, especially when it comes to materials with kind of really desirable properties for dental and commercial applications. But it really just depends on the chemistry and the formulation that you're using. I wouldn't say one is necessarily better over the other.
Okay, great. The next question is, why does water, saliva in the oral environment affect the strength of photopolymer resins?
Yeah, it really depends on the resin itself. You know, as we showed with Trusana, the strength really isn't affected too much. But polymers in general are a network, right? And you have some free volume that's associated in that network. And depending on how tightly cross-linked that network is, you have water molecules, which are smaller in comparison, that can diffuse into the polymer and potentially interfere with those polymer bonds, just depending on the chemistry that's used. So the water sensitivity really depends on the chemistry that's used in the actual product that you're working with.
What about workflow with Trusana?
Yeah, so the workflow, the comments that we've gotten so far from different beta labs are that the workflow is simpler than other resins. It's more straightforward. It's more streamlined, takes less time. But as far as the steps, when you get Trusana, you'll do the print according to your printer's manufacturer's instructions, you know, loading the file, et cetera, preparing the resin. And then you will do a simple 5-minute IPA wash once the part is completed off the printer. You then place the parts for 8 minutes on one side in UV cure box. You take them out, turn them over another 8 minutes, and then you have a 10-minute heated water annealing step at about 80 degrees. So you essentially put your part in a plastic bag, you seal it, and you submerge that bag into the water bath for 10 minutes at 80 degrees. And that's it.
Okay, we have another. So this attendee wants to know if Trusana printed denture teeth can be bonded to a milled denture base, or does
Yes.
it have to be a printed denture base? And if so, what is used to bond the teeth to the base?
That's a great question. So in short, yes, you can bond Trusana to other printed Trusana dentures, other printed teeth, or excuse me, dentures, and then also milled dentures. And when we launch, we'll have some suggested workflows for that and what bonding agents to use.
And the next question is, what is the post-processing protocols for Trusana?
Great. So yeah, I just covered that in the previous section, but real quick again, it's basically a quick IPA wash. You'll then do an 8-minute UV cure, take the part out, turn it over, another 8-minute cure, and then you'll finish with a 10-minute 80-degree water annealing step.
Excellent. Again, another question on the teeth. Will there be dentin shades?
Sorry, say that again?
Will there be dentin shades? Can they expect dentin shades?
So with the shades, we're actually going to have 6 different tooth shades available and 4 different denture-based shades that are available. So yeah, and those include all of your traditional tooth shades, and then also in the denture-based shade, an ethnic gum shade as well.
Excellent. There's another question. Any reason why the Flexural modulus GPA slightly increased from 48 hours to 14 days in a wet environment with Trusana?
That's a good question. I would say probably no particular reason. You know, I would say the numbers are all within kind of a margin of error. But really what that shows is that the performance is quite consistent. I think it was the difference between 3.4 and 3.6 or 3.4 and 3.2. So all pretty much hovering around the same performance. And
Okay,
then and those measurements, oh, just sorry, one other point. Those
sure.
measurements are derived from multiple test specimens that are averaged to get a good tight tolerance range. So it's not like, you know, that was one test bar and shown. Those were actually averaged from multiple different test bars.
Okay, one more question. They want to know if Trusana teeth resin, is it validated for permanent crowns, temporary crowns, denture teeth in a denture base?
Yeah, so by the time we launch, it will be fully validated for very specific applications like those that are mentioned. So I invite you to follow social media for updates on those different applications and the validation.
And the next is, where do you see photopolymer printing technology headed from here?
That's a great question. So for me personally, I think it's really a lot about the materials. I think, you know, with new chemistry like Trusana, as well as other chemistry that's being developed by others, that's really where we're going to get expansion of these clinical applications as well as other industrial applications. So I think with new chemistries, new creativity there, that's really going to yield some things additional to what we're already seeing. I'm also excited about multi-material and multi-color printing technologies. You know, I mentioned that for Inkjet, which provides a lot of different ways to, say, print one part with different multiple colors. Also, folks are working on that with respect to DLP and other UV type printing. So I'm really excited about being able to use multi-materials in printing of 3D printed parts.
Okay, and there is another question about FDA approval. They want to know if the teeth resin is FDA approved.
Yes, so it is, and the approval will be fully in place by the time that the resin launches.
And how does Trusana stack up compared to other resins in the category?
Yeah, it's a great question. So obviously, I showed the mechanical properties, you know, the flexural modulus, the strength, the water uptake, as well as the wear, where we're outperforming those in the category. The feedback that we're getting from beta labs is that the workflow is a lot simpler. The resin, the parts look great. They look better than other resins that are being printed with. They print in a good amount of time as well. So overall, getting some really positive feedback and looking forward to seeing more feedback from folks that adopt the resin and use it for their in their laboratories as well as chairside.